Okay, thanks. Indeed, my name is Develder. I'm from Ghent University, Belgium, also affiliated with Eindhoven, which is sort of an inter-university institute. And indeed, I've been working on applying data analytics and machine learning in the smart grid field, so that's one team I'm leading. And aside from that, there's another team working on natural language processing. But obviously, today I'll be presenting mostly work of the first team, and indeed presenting some of our research, including the EV charging part, of applying these machine learning techniques in smart grid areas. So I don't need to introduce this too much, because before a friendly audience. But yeah, as you know, the main challenges that our grid, or power grid is facing is both the introduction of renewables, which are intermittent, you cannot control and so on and so forth. It's one side of the story, and then there's the other one of increased electrification, including EV charging. So to address these challenges, you can introduce various technologies. For instance, introduce some storage, which can help you sort of store the energy and then reuse it at the time you need to. Or you can control or try and control the load, because you no longer have that much control over the generation part anymore, using demand-side management and so on and so forth. We've also been talking about new services, business models. Previous talk was an excellent introduction to that. And of course, for that you need ICT infrastructure, and that's why I, as a computer scientist, am also active in the power engineering field, basically. So that's where we are, and as today I'll be focusing on two aspects. My talk will be divided into two parts. The first will deal with the EV charging part, knowing the behavior, and then trying to control the charging. And the second part, if time permits, will delve into another sample application, more on the distributed generation side, which, because the application there is some recent work of a recent PhD student who has been working on fault identification in PV panel outputs in residential areas. So rooftop PV panels, basically. Okay, so that will be the talk. So I'll start first off with the EV part. So what I'll be eventually talking about is controlling the charging process. And again, we'll be using this technique that was also mentioned in the previous talk, which is reinforcement learning. But basically, I'll split this into two parts, two steps. Firstly, before trying to control the behavior, obviously, you have to have some insight on how do people charge their cars, when do cars arrive, how long do they stay there for, how much charging is actually happening, and so on and so forth. And hopefully, there will be some flexibility, meaning that you can shift around basically the time the car is being charged actually. So the first step, you see a couple of papers listed here. By the way, the presentation is already on my personal website, so if you need a PDF version and want to check these references in more detail, you can find the information there. So the first step we took a little while ago, because initial work was performed on that. So one of my, actually was not the first, but the second PhD student in my team on energy. So we characterized, or we looked at how do people charge their cars. And for that research, we basically have access to new data sets, a smaller one, which we, to some extent, collected ourselves in this frame of a back then research project called iMove. That was residential charging, so people got an electric car, charging infrastructure, and these sessions were recorded in terms of when did people plug in their car into the grid, how much charging happens, and when did the car leave the house, basically. So in the project itself, there was no control, meaning that as soon as you plugged in the car, it started charging. But obviously, we have also the traces of the actual charging happening, so at some point it's finished, and then the car stayed on, meaning that there's, so this time that the car is there, it's no longer charging. Basically, you could have shifted the charging to that side. So the whole goal of this study was really get insight in how long are cars connected for, and of that time connected, how much time were they actually charging? Because that gives you the information of what is the time frame I can play around with, what is basically the flexibility that I have to shift around this charging, which will then do the next step, being the actual control. Similar data, but on a larger scale, was also collected in the Netherlands, and we basically use a lot of data from there. So it's from an organization called ELAT, which is a sort of an it's an organization that was founded by multiple DSOs in the Netherlands to basically roll out charging infrastructure, collect data, to learn more about how people are or would be using this infrastructure. So basically, the analysis, of which I will be showing the results, will be mostly from the ELAT part. So the first step what we did is just looking at what time did the car arrive and what time did it depart. And each of these dots and those spots that you're seeing before you now represents such a single charging session. So the x-axis we have the time of arrival, the vertical axis we have the time of departure. And what we did then is basically apply some existing clustering algorithm, scan to be more precise, to get insight in what types of sessions do we see, and this is what these colors represent. So you basically see three colors, so three types of behavior, so to speak. The blue one, those are points close to the diagonal, which means that the departure time is not that far off from the arrival time. So these are relatively short sessions of a few hours at most, let's say, so close to this diagonal. Throughout the day, as you can see, and then we have two other colors. One, the orange one there, the blob of the lower right corner in both graphs, with arrival times, as you can see, in late afternoon, evening-ish, and departures, obviously, the next day in the morning. So this is basically nighttime charging, and this is, so we see those, this behavior also on the residential side, of course. The third type of charging sessions is, this is yellow. Okay, I'll just continue if you have difficulty understanding me, just raise hand and I'll stop for a little while. So the third type that we see there is this yellow cluster. So as you can see, this is arrivals in the morning and departures in the late afternoon. So this is daytime charging. And as you can see in the residential case, time move data, on the right hand side, we obviously do not observe this because people typically, when they arrive at homes at night and not in the morning, right? So that's why this color is not present in that graph. So this is the first step, and then obviously we try to get some insight for each of the times of the day, which is here on the x-axis. What is the amount of arrivals that happens at that particular time? And we looked at it also, as you can see, from two different time frames, so two types of days, basically. Weekdays, which is orange bars, and then weekends, which is the blue bars. And you see some a priori possibly expected behavior. So for instance here, on weekdays you see peaks at the morning, evenings, and lunch breaks basically, while on the weekends is more distributed over the day for the blue sessions, so the shorter ones. And then we see also some shifts basically towards later times in the weekends for the other clusters. Note that I dubbed these charge near home, is sort of the nighttime charging work. Near work is probably, and that's what we found out from talking to the people that deliver the data, is some of these charging sessions are basically closely or nearby public transportation, especially train stations. So this is both basically people commuting or doing a weekend trip, right? So that's why we see also this shift to later times. So we did a whole bunch of more analysis, more deeper fitting solutions to that, to be able to generate also data. I won't go into details here. If you need for your studies this kind of data of EV arrivals, departures, which you can use for what-if analysis or actual control studies. Manu, another PhD student in the team, has actually worked on releasing Python code that can generate sessions, because we were not cannot share data freely with you, but we can generate or share the fitted distributions, and these are included in the software there. So if you need this, just say you could use those. What did we do with this data? You see two other papers listed there, which I won't go into detail in. But basically, using this data, the main goal of obtaining these models, obtaining these insights, was getting insight is what is the amount of flexibility. So in other papers, we proposed metrics of how can you quantify this flexibility. And in another one, where we actually control that flexibility, we also studied of the available flexibility, both in terms of on the scale of time, and how much can you defer charging, how much time flexibility do you have, and how much of that time flexibility window that you have gets exploited. in various control strategies. We also provide the metrics for that. On the other side, you have the energy dimension and how much of your charging budget, let's say, I have to charge a few kilowatt hours. I have to put that energy in my battery. How much is pushed out of the business as usual framework? Business as usual meaning you charge as soon as you arrive until complete. We also investigated how much of that flexibility gets basically exploited and how much the control strategies would use that flexibility. And what we've seen is that on the time scale, indeed, in various scenarios, we see that the final part of charging does get pushed until the very end, but the fraction of the total energy that you need to put in your battery is only a relatively small fraction that gets pushed outside of this business as usual frame. Which means that people, and the first worry of people would be, what if I leave earlier than anticipated or something like this? So meaning that only the fact that only a fraction of your energy is basically moved out of the charging as fast as possible scenario, so to speak, means that even if you leave earlier, you will have had a substantial fraction of your charging completed, so you don't have to worry that much about sort of not having enough range or something. And here on the bottom you see the kind of questions we can answer by studying what if scenarios using that data. But as I said, I won't be going into too much detail here. I want to move more to, for me at least, more interesting aspect, namely how do you control the charging? If you have, for instance, a public parking space, let's get tens or a few tens of charging stations where people and their cars come and go, how can you control the charging to meet a certain objective? And again, you see some papers listed here by Hoyt and Manu, where you can find the details of what I'll be presenting next. So, first of all, you have to decide, obviously, what is the objective I want to meet. You have various options. A very straightforward one is I want to limit the maximum power that I would need, meaning that instead of having sort of a curve that might look like this, with certain peaks at certain times, basically when people arrive. So this is for the case of residential charging, I think, looking at the time scale here. But basically what you want to do is exploit flexibilities with the charging and to basically flatten the load profile. So that's one use case, and that's the one that will be focused on most in the studies presented next. Other scenarios that you can obviously think of is, for instance, this local energy community kind of scenarios. You might want to balance the charging of your vehicles to the available renewable production. That could be another scenario. And then there's also some technical reasons from the grid operators that might lead to other objectives. But as I said, in the case studies presented next, I'll be assuming the first one, namely that you want to sort of level out the load over the amount of time. So ideally that will be a flat line. Obviously, depending on the flexibility available, you might still have to deviate from that, obviously, because flexibility doesn't allow you to basically achieve this flat line perfectly. So, what is a problem statement? We are, as I said, what our algorithm, that I'll be presenting next, that we'll try to do is coordinate a set of charging stations. You could think of the parking scenario, or you could also think of a community where these charging stations are spread around a bit geographically. But basically, I want to have a control system that decides for a bunch of electrical chargers when to charge the cars that are connected to it at any point in time. So we'll assume slotted way of working. Let's say you can think of using every 15 minutes, I'll make a decision. I have maybe 20 cars connected, but I'll be only charging, let's say, half of them in the next 50 minutes, and so on and so forth. So that's what you need to do. What is the information that the algorithm gets as an input? We assume that for all of the cars present, we know basically when they arrived, but we also know when they will leave. That's what we assume. So either you can learn this from sort of monitoring the users, or you can have a very simple interface where they sort of indicate, I'll be staying here for 3, 4, 5, 6, 7 hours, whatever. That's one thing we assume. So the arrival and departure times of the cars that are there. We don't know about, or our algorithm doesn't know explicitly of future arrivals, so we don't get a default notification how this car will arrive in 4 hours. We don't know that yet. But the other thing that we do assume as knowledge is basically the state of charge of the battery, and from that also we can obviously then know how much charging still needs to happen, so basically the amount of kilowatt hours or the amount of time slots, if you know the charging rate that the car will need charging. That's what we take as an input, and then, as I said, each time slot, one after the other, the system will decide for the cars present, I will charge this or not, and so on and so forth. And as I said, the objective is basically, instead of charging up an arrival as fast as possible, I'll be deferring some of the charging within the time frame of the car being there, that I can, and I will exploit that flexibility. So that's what we're trying to do, and as I said, we used reinforcement learning. Can I see a show of hands of who's familiar with reinforcement learning? Okay, quite a bit. So I'll move rather quickly, because I have a few slides just explaining the concept. For those not familiar with it, it should clarify at least the ID. So what is the ID? We have an agent. You can think of a game, or in our case, this charging controller, that needs to take actions. So what is our system model? Basically, the actions to decide what will I do, what will my agent do, and again, what move will I make, or in our case of EV charging, which car will I charge. Obviously, you need some input information to base that decision on. That will be two parts. First of all, the state, which basically characterizes the state of the system. So it might be where you are in the game, where other objects are. In our case, it means the neighbors I just discussed. That will be sort of observing the system and getting information of what state the system is in. And then to pick the best action that you'll basically do on the basis of rewards that you get. At least that's one way of framing the problem. So in game, it's basically the points you gain in our electric vehicle charging problem. It will be how close is my route to this sort of flat line. And this is basically, this process happens each time step one of the other. So the agent looks at what is my current state, what is the reward I got from my previous action, I will decide on the next one. This will then impact, obviously, the state and the reward in the next time step, which is what the system or the system model will provide, and so on and so forth. And so the idea is to learn a policy. And what is a policy? Basically, this is the function that maps the current state to the action I'm going to take. And I want to develop the policy that sort of obviously maximizes the long-term reward. That's basically the idea. Typically that's framed in what is called a Markov decision process. So what is Markov? The Markov assumption is basically that you don't need to remember the whole past to make your decisions. Basically it means that you can look at the current system state, or a short history, typically just the current state. Your state representation basically contains everything you need, and you don't need to remember the states of previous time steps. That's basically what this assumption means. So the goal is indeed to learn this function, a policy, which, given the current state, decides what is the action to take. That's what we're looking for. And one way of doing it is Q-learning. What is this? Well, the point there is to try and learn a function that gives you, for in a given state S, the value, basically the benefit, of taking an action A. And then, if you know that function, what will the policy be? Well, you will decide that action, given the current state, that returns the maximum benefits. So basically, you look for the action that maximizes this function. That's how we will use this function. Now, how can you learn this? Well, the goal, obviously, of this Q function is that it represents the reward that we'll get, not just the next step, but over long horizon, basically infinity. Because you want to optimize the system for the overall system benefit, not just the greedy approach that maximizes your profit, your reward in the next time step. So how can you learn this? Well, you start from zeros for all of the actions, for instance, And then you iteratively update the function. So you see here of your previous iteration, that's the values you start with, and then you take sort of a weighted combination of that previous value, what you believe previously, for the value of that action in that state to be, and then you update it with this function, so itself as a learning factor. But what I want to stress here, so what you're trying to do is you want to calculate the long-term reward, so that's why the immediate reward is there. So what is the reward of this time of taking action right now? Plus, obviously, the long-term reward. How can you model this? Well, you assume that the next from the new state, so S prime there is basically is the state that is a result of starting from S and taking action A. What will be your next system state? Assumption is there. Obviously, you follow your policy and basically take the best action, which is this maximum. So that's basically you try to update this value with the immediate reward and the maximal future reward by taking the best policy. That's sort of the bottom line idea of new learning, and that's basically we sort of apply in one way or another. We actually use the iteration, which learns this function not by just this single value approach, but using a function like approximators. But yeah, I won't be going into that level of detail. I hope that at least the idea of reinforcement learning is a bit clear now. So how do we apply this on a TV charging case? So we need basically to define how do we model our state of the system, and then given that state, how do we formalize the action that we'll take. Now, what we want to do, as I said, we want to control a bunch of charging stations. So we basically want to represent that state in a scalable fashion. And ideally, what we also wanted to do, and that's the definition of the state that is on the slide. What we also wanted is that this, if we learn a policy for, let's say, a case of just 10 charging stations with a certain arrival and departure pattern, we want to also be able to apply that learned policy on another system with a different number of charging stations. Obviously, still assuming that the arrival and departure statistics would be the same. So that's why we eventually came up with sort of a normalized, you could say, state representation. How does it work? Basically, we don't want to, there's two aspects there. One is that we don't want to represent each and every of those discrete number of charging stations. We don't want to model each or specify the state at each individual charging station. So we basically group them in sets of, or the vehicles there, we group them in bins, and this is this matrix representation there, where we have, let's say, 2 dimensions. One is we bin the amount of time left, because each session, each car that is currently in the system, as I said previously, we assume 2 things. We know when it's going to depart, so the remaining time it's going to be there, and we also know what is the remaining charging that needs to happen within that time frame. If we, for simplicity, assume that the charging rate is the same for each and every car, the amount of charging can also be expressed in the number of time slots I still need to charge. So that's so it's basically 2, let's say, durations. How long is the car going to be here? And how long is that car of that time? How much time does it need actual charging? And so these will be the 2 dimensions that we consider in this matrix. So the upper left corner is basically the amount of cars that will still be there for 1 time slot, let's say, and actually also need that time slot to be charged, and so on and so forth. So if we move right, means, so if we go right in this matrix, means that the requested amount of charging remains the same, but the time that the car will be there increases. So going to the right means we have more flexibility. So we basically count for each of these cells in the matrix how many cars are there for 2 time slots in each one of charging, and so on and so forth. So obviously there cannot be any cars in the lower part because it needs more charging and it's going to be there for, which is not something that should happen. But basically, so that's why these grade cells there are shaded. These are the ones where we can have actual cars. And then we scale this matrix basically by, so we count the number of cars. So let's say we have just one car in the cell. So C1 and C2 represent one car. Let's assume for this simple example there's only two charging stations. We'll sort of scale this matrix by dividing it by the number of charging stations. So it means that they're both will be occupied because they sum to one, and half of them is in one state and the other one is in the other. So that basically represents the state in sort of a normalized fashion, and we'll later show that by doing that and also by sort of normalizing the actions, we can indeed learn policies in smaller systems and apply them on larger systems or vice versa. Assuming still that the statistics of arrivals and departures and the charging requests are similar. So that's the state. So if you know that state, you can basically enumerate all of the possible actions, because how do we frame the action? It's the top part of the figure. So if you understand how this matrix works, basically you realize that all of these diagonals or the parallels with it represent cars that have the same amount of flexibility, right? It's the same amount of time slots that you can choose to charge a car. And obviously we'll want to treat all of the cars with the same flexibility. That's just what we want to do in the same way. So basically, in this very simple example, that we need only for the three diagonals here, we need for each of them, what are we going to do? And again, we normalize that in terms of how many, what fraction of the cars in each of those flexibility cases will be charging next time slots. So our action will be a factor, so we can either charge one of them, so that the 3-0 stays there. We can just charge one of the two cars, because in this case we only have two charging stations. So there's a middle action and the final action is to charge one of them basically. Then you can, for each state, basically enumerate these possible actions. From that, you can calculate what will be the next state. So you can basically draw these decisions trees with all of the possible actions to take, assuming no other cars arrive, for instance. And that's basically what we do to train and learn this Q function. We basically do not enumerate all of the cases, but we sample from these trees, and then we learn what is the reward and how should we charge them. So that's the general idea. So I'll stop here in terms of providing details about the algorithm itself, and you can find out that in our papers. So what are the lessons learned, or what are the research questions that we try to answer by learning this and then simulate the behavior? First of all, we need to specify what is the input and what assumptions do we take, basically in terms of arrivals. For that we used data from the SNIPPET. Also for this sort of proof of concept, as you can see, we chose decision time slots that are quite long, way longer than in reality. That was just to be able to quickly learn the algorithm and also be able to compare it to an optimization approach where we provide all the information, also the future arrivals, and then we could, for those cases, still calculate what is the actual optimum decision, the best that you could do, assuming that you know everything unfold also about the future arrivals. And then we want to compare our reinforcement learning approach to that, for instance. One other detail is that instead of using the reward type of formulation in reinforcement learning, here we sort of, instead of maximizing the reward, we here minimizing cost. And cost is basically, as you can see, it's defined there as the squared power with a given time slot. Because if you try to basically minimize the sum of squares over a long time horizon, it means that you're trying to find just a mathematical way of expressing the solution objective. But what are our conclusions? Well, we see that compared to business as usual, which means charging upper arrival as fast as possible, we indeed see we can flatten the load quite a bit. It translates to this sum of square cost reduction in the amount of 30 to 40%, as you can see there. So that's obviously the least we wanted, to do better than as fast as charging as fast as possible. The good news is that we are relatively close to the optimum, which has extra information compared to our algorithm, being that it also knows of future arrivals, when cars will arrive, and so on and so forth. There was another common sense baseline that we compared against. That's the bottom bullet there. Obviously, if you know for each individual car how long it's going to be there, how much charging it needs to be, from that car's perspective, the best you could do to reach a flat line would be to smear out that charging on that single car. Right? If you do that for each single car individually, that's sort of a baseline heuristic, which obviously also performs better than as charging as fast as possible. But luckily, and that's obviously what we hope for, our learning approach still does quite a bit better. Now, these are some details. Yeah, the performance, obviously, it depends a bit on the exact arrivals happening, which could change from one time to the next. So basically, here you see simulations of the extended full year. And you see indeed that, note that these costs are normalized. So one is the optimum, and we should get as close as possible to that line. You see there are blue approaches to get there. The heuristic part that I mentioned would be somewhere here, it's about 20% above. So that's basically just showing that it works. And the other thing is that I mentioned previously is, yeah, does this scaling up, meaning learning on smaller system, and transferring to a larger one where the car arrival and departure statistics are the same. This basically shows that it works. So the blue line goes up a bit if we scale up. So it means that we train on a system with 10 cars, then we test it on more than 20, 30, 40, and so on and so forth. Charging stations, we see that it gets a little worse because the line goes up a bit, moves away from the bottom a tiny bit, but it basically still performs quite well. So that's good news in the sense that we can, because obviously to train this reinforcement learning approach, if you can train it on small systems, it becomes faster. I think that should be good. So that's basically the summary of the results here. So this reinforcement learning approach does seem viable. I still need to test it, and also other scenarios, for instance, the renewable balancing case. I also used other approaches of reinforcement learning to other cases of exploiting flexibility. An important one there is building heating. So it actually we are also doing that in gas-heated buildings, so you can apply the same type of ideas also during electricity scenarios where you want to exploit flexibility with the energy. Okay, so that was part one. I see that I still have a bit of time left, so I'll quickly also illustrate another case, which is something completely different. So the previous one was on flexibility and controlling that. The application here is just basically a monitoring application, but also we'll be using neural techniques, as we'll see in a minute. So what is the case? What are we trying to do here? Well, the thing is that especially in Flanders, but also regions, and also in this case of this energy community story. Basically, people are generating, or at least some of them are generating their own power, and a popular source there is rooftop solar panels. But the way they are deployed today is basically fit and forget, and you put them on there, and as soon as something comes out, people don't care that much, meaning that they don't detail monitor what's going on and if there's anything wrong with the system. Some of these faults could be minor, other ones could be more dangerous, as you see in the picture. But the thing is, installing a monitoring system by adding extra sensors for just residential consumers, this cost is quite high, and the benefits are not that clear. So people basically, it's not being done today. That's basically what I want to say here. So what we looked into in this project was, can we use a data-driven solution that can identify possible faults, meaning that the PV output power is not what it should be, given the current irradiation of the circuits and so forth. Can we do that in a data-driven way, using data that's already available today? basically inverter outputs in terms of voltages and currents. That will be the main source of information. Without installing too much extra sensors locally. That's what we're trying to do here. So the first method that we use here is basically analyze the time series of the data that we have available, meaning this voltage and current, and use recurrent neural networks to do so, to process those time series. Again, details are in the papers cited here. So, but what is the general idea? So, what is the input? The input is time series of your current and voltage. Obviously, to decide the power coming out of my PV installation is what it should be or not. What it should be depends on the current weather conditions. So we also input some of this information, temperature and irradiance. And also obviously the orientation of the panel basically will influence that. And what we want to do is, by just processing the time series of these sources of information, we want to classify, first of all, there's a fault or not, but if it's a fault, we want to also identify some different types. You see some listed there. Some are more serious, like short circuit, or others are just sorting. Basically, there's dust or sand or whatever on your panels. That's one thing. And secondly, besides identifying there is a fault, we also want to assess what is the impact of this fault on my output. Would I, if this fault is solved, would I have, let's say, 10% more, or just 5%, or 50% more? What is basically the power that I lost due to this fault? That's basically what we call severity. So these are the two outputs. So time series, how can you deal with them? If you want to use data-driven methods, neural networks, we'll be using recurrent neural nets. Maybe can I have, again, a show of hands of who's familiar with RNN? 1, 2, okay, about 12 people again. For those that are not, brief intermezzo, what is the ID? So basically you get a sequence, a time sequence, and you input X, and then you have to have some outputs which could be tied for each of related to each of these time steps, or just an overall output. Let's focus on the input. If you want, first of all, if you would use just plain feed-forward network, which means you put in some features and you have some neural layers and there's an output layer that gives you the output. In our case, it will be the classification, is there a fault or of a given time, and secondly, what is the severity. Basically, you would need to design that network for basically the input of your time sequence. How long, what is the history of my time series data that I will consider? Will it be the past 5 hours, 6 hours, a day, 2 days, 2 months, whatever. So that will impact it, and the fact that at each of these time steps, these features, so each of these axes would be a combination of this voltage, current, and weather information, and so forth for that particular time step. Obviously, these features are of the same nature for each and every time step. But your neural network here is not, it's basically agnostic, and you can sort of not rely on this a priori notion that you have as a human. So basically, to decide, first of all, this network will have a lot of parameters, depending also on the size of the input time series you want to consider. And a priori, this network will have no notion that basically all of these time steps are somewhat, and the features that you put in there are of the same nature. So one way to do to sort of exploit the fact that these various time step factors or features that you feed in are the same nature is to define just a single block, which is here represented by this vertical bar there. And the important thing to realize here is this: the parameters of all of these blocks will be exactly the same for all of the time steps. So meaning the number of parameters, even if you use the same sequence length, will here be basically a fraction of that length lower than the previous case. But obviously, you don't want to process these time steps independently. You want to sort of remember what's happening. So that's why we see this extra input here at this stage, which is the hidden state, as it's commonly called in this context. So aside from the input, for the output, the Y at the top there, which will have a space for each and every time step. We also have a second output, which will be this hidden state, which will feed in to the block the same functional operator at the next time step. So basically we can share the parameters of these blocks because they will be the same for each time step. And so we will have a lot less parameters, and then to produce the output, in our case, we need to do classification. So we can use either the hidden or the output state of the final step, or we can sort of pool all of these steps together, max pooling, whatever. Meaning that also, we don't have to redesign the architecture if we want to extend to longer time steps. So that's basically the idea. I'll skip the math probably. But it's just detailing one block out of it, and basically what the functions are that define your output, y in its hidden state, is basically a non-linear function applied to a linear transformation of your inputs, which is previous time steps hidden state and current time steps. And then, so the recurrent part obviously refers to this hidden state that is passed on from one time step to the next. This is sort of the basic idea. More complex architectures have been developed, like LSTMs and GRUs, to deal with some of the problems of these very simplistic first approaches, as they are sketched literally here on the slide. So that's the technique we're using. So back to our problem, we have all of these time series. So basically each time step we have a bunch of values for each of these inputs. We feed this to a number of, as you can see, GRU layers, so it's a more recent RNN architecture. And then we have some feed-forward layers to output the classification table and also the severity, which is a real number, so it's more of a regression problem there. So using the exact information about temperature and gradients at the location leads us to pretty good accuracy, as you can see, 96 something %. But obviously, as I said at the start, we want to avoid installing even these kinds of sensors. So the next thing we did is, that is still a confusion table, I won't go into detail. The next step was, can we do away with these local measurements and a proxy for those, which are readily available, as information from satellites. Obviously, satellite information is not for your exact address, it's more for a region, so it's less accurate. So if you look at the actual irradiance at a certain place, the actual temperature at a certain place, compare it with what the satellite says about that region where the place is located in, then here you can see sort of the relations between on vertical axis the satellite data versus the actual one. So ideally, it should be on this diagonal. So what you see here is that you have generally a bit of overestimation for the irradiance and a bit of underestimation for the mean temperature at that location. But still close enough, maybe. That's what we wanted to investigate. So what we did is we used the exact same setup, but now instead of feeding the time series for the actual location, we feed in the satellite information. We see that the overall accuracy drops, but it's still reasonable, 86%. And the confusion matrix changes a bit, and the major change is now that the no-fault situation is confused with soiling. Soiling means there's dirt on the panel. So basically, it means that the model sort of interprets, or as a result of this overestimation of irradiance by the satellite, it thinks, since the actual irradiation is lower, it's lower also than what the model expects. So we see indeed a confusion with this soiling case. That's basically what we're seeing here. So then also for the severity, we're doing quite good. I won't go into details here. So that was the first approach. You see that we still have a few minutes left. So then the next thing was, can we sort of, what our intuition was, how can we estimate whether something's going on or not, going wrong or not at your PV panel? Obviously, if you have a large deployment of these PV panels and you have neighboring houses, those neighboring houses' conditions in terms of the weather will be more similar than yours, than what the satellite says. That was the intuition. So our line of thinking was, what if we do not have only data from a single rooftop PV installation, but from multiple in each other's neighborhoods? Can we, by just comparing those, not also try to infer, or based on that comparison, basically, can we do this classification or identification in the first place of faults, not also based on just comparing neighboring houses. That was basically the intuition. And how we did this, we basically used a technique that is called graph neural networks. So basically, the problem statement now is we don't have just the information from a single house, but we have this information about voltages and currents, and we even don't use that information at all anymore. We just have these time series, not from a single house, but also from neighboring houses, and we do assume that we also have some information about how far is house A from house B, and so on and so forth. So basically, we represent these houses in a graph. The nodes are the houses, and the information we have of the house would still be this sort of time series, which you can push through GRU, and then we have sort of a representation of that house's state of the, let's say, past 24 hours, for instance. And then these would represent in our graph the nodes, and then we have also obviously the edges. So the edge information would capture how far is this house, its location from the next, and so on and so forth. For the introduction to graph neural networks, I just will skip this. Again, but basically the idea is that you have a representation of nodes and links, and then you have some functions of transforming this information, combining it, which would be based on the connectivity of the nodes to get all the representations for the node by adding these graph layers. So that's what is meant by this lower left box in our system sort of configuration. And then for each of the houses, we get an output in terms of severity and type of fault. And we see that by combining this information, but only the voltage and current, no other information at all, we, and this was kind of a surprise that this worked so good actually, we also reach accuracies of 80%, which is pretty good, I would say. So that's basically the result of this segment study. So since we're approaching the end of the time I was allotted, I'll try to wrap up. So what I try to do is give you some insight on what are the kinds of methods, techniques, neural networks, reinforcement learning, graph neural networks that we can use, and what we can use them for is basically both just analytics, getting insight in what's happening, which can then, those models coming out there can help you to try formative scenarios. For instance, by clustering these behaviors. Obviously, in your data, you have a certain fraction of each of these clusters. If you have them all, you can sort of vary the proportions of these different behaviors and see what will be the result if, and so on and so forth. Control this reinforcement learning, and then also some time series processing, basically. So, I want to thank you for your attention, but also the team that's working hard to build all these results and for having produced results here. And I also want to acknowledge funding from the European projects which are listed below. That's it from my side, so thanks for your attention, and if you have questions, I'll be happy to take them.